Hello and welcome back. We have been talking about the cluster expansion. So, we will continue that discussion till we derive the equation of state. So, we will talk about the cluster integrals and the virial coefficients, and finally, the equation of state at a given level or at a given order. And it is important to understand that we are calculating the partition function for an interacting gas, which is the molecules of the gas are interacting pairwise. Okay. So, the interacting partition function is I write interacting partition function, but it means that the partition function of the interacting gas. Okay. So, this word is to be seen carefully. So, we write it as Zn Vt or you can write NVT with the N inside. This is equal to sum of all the distinct graphs. Okay. So, this is important, and we are talking about a L cluster graph. Okay. So, L is the number of participating clusters there. So, say we have given this example, say a 5 cluster graph looks like you have a 1, 2, 3, 4 and 5. And let me show this. So, this 1 and then there is 1 4 and 3 4 and 1 2 and 1 5 and 2 5. Okay. So, this is a 5 cluster graph which can be written in terms of the expressions or the expansion in terms of these f functions. So, there is d cube r 1, d cube r 2, d cube r 3, d cube r 4 and d cube r 5, and then we have f 1 2, f 1 3, f 1 4 and f 1 5, f 3 4, f 2 5 and so on. Okay. So, that is a 5 cluster graph, and we have to sum over all these distinct graphs, and in order to show what is distinct, we have shown this as an example, which are identical and non-identical clusters. So, in doing so, we can show that there is for example, 1, 2 and 3, and we will write these things and then put the connections. And wait till I put the connections. So, this and this, this and this, but this is not the same as this and this. Okay. So, the first 3 are identical, whereas the last one is has to be counted separately. So, how do we write the cluster integrals? So, we can write the cluster integrals including all these clusters as let us write them as BL Vt, it is equal to 1 by L factorial lambda 3L minus 3 into V into sum of all these all possible L clusters. So, once we find this, we should be able to find the partition function. Okay. So, this prefactor is important and it is chosen such that your BLVT is dimensionless. And you will see that this lambda to the power 3L minus 3, well, lambda is of course the thermal de Broglie wavelength, and this for L equal to 1, this there is no term of lambda. From the second term onwards, there is a lambda cube and then there is a lambda 6 and so on and so forth. We will see that soon. Okay. And so, now how do we actually calculate these integrals? You see that if you keep one particle fixed, okay, then and carry out the integral over all the other particles, okay, and so your Fij which was considered earlier, and this Fij has a finite range. And why does it have a finite range? Because the interaction is neighboring, or it involves neighboring molecules. So, this has a finite range. So, this integral only extends over a few sites. Few sites, or if you do not say sites, over a few molecules, and basically over a few sort of small range. So, this means that over a small range, and this is for if we keep the position of a particle to be fixed, say at R1. So, position of one particle is fixed at R1, and now what we do is that, or you can call it as Ri, Ri to be any particle. Now, when you integrate over or sum over all Ri, that brings in a factor of V, volume, and that volume would cancel with this volume that you see in the denominator in this expression for BL. Okay. So, for example, let us see some of the B's. So, for example, a B1, the first term is equal to 1 by V, and this does not involve any link. So, this is equal to 1 by V d cube R1, which is equal to 1. So, B1 equal to 1, and we can calculate B2. B2 is equal to, so you have L factorial. So, B2 is 1 by 2 factorial, and we have a lambda cube V, and then we have connection of this kind, which is 1 and 2 connection, which is equal to 1 by 2 lambda cube V, and then we have this integral, which is d cube R1, d cube R2, and F12. And this is equal to 1 by 2 lambda cube V, and d cube R1 2 and F12. This is written as, so now I have d cube, so 2 lambda cube V, and we have this d cube R f of R, and this of course can be written as so in the limit V going to infinity, this is 1 by or rather this if we change this d cube R to 4 pi R squared dr, then we have this as 2 pi over lambda cube, and we have 0 to infinity, and we have R squared dr f of R. Okay. So, we will show these calculations explicitly when we go and finally calculate the partition function. So, this is that, and then you can sort of put a preferred form for f of R. All right. So, let me see the next one, and this is B3, which is 3 factorial, which is nothing but 6, and it is lambda 6 into V, and then you have all those terms. Let me show them by these graphs. The B2 I have shown it by expressions. So, let me show these by graphs, and plus 1, 2, 3 plus 1, 2, 3 plus 1, 2, 3 and so on. So, all these distinct graphs have to be taken into account. So, we have this, then we have this, then we have this, and then the other non-identical. So, these 3 are of course identical, which is what we have said, and this is of course the non-identical, but they have to be counted separately. So, this is like F12, F13, this is F12, F23, this is F13, F23, and this is F12, 23 and 31. Okay. So, these are the B3 terms, and they can be calculated. Let me show the calculation of B3 explicitly. So, 3 factorial is 6, and then lambda to the power 6 V, and then we have d cube R1, d cube R2, all these coordinate integrals have to be written, d cube R3, and we have these F12, F13 plus F12, F23 plus F13, F23 plus F12, F13, F23. This is the form that we have written down earlier in terms of these things, these diagrams, and now explicitly calculating them means that we have these d cube R and d cube R prime, and we have these 3 as identical. So, they can be written as f of R and f of R prime, and plus f of R, f of R prime, and f of R minus R prime. Okay, so, that is the last term. Okay. So, these are these things, this expression for B3, and this is nothing but equal to 6 lambda to the power 6 V, and then we can write this as 3 twice of lambda cube B2, because you see this expression appears in B2. Okay. So, this is 3 into 2 lambda cube B2 square, and now we have a d cube R, d cube R prime. This we cannot do anything, we have to just leave the last term, we have to leave it as it is, and f of R minus R prime. So, this simplifies to a 2 B2 square plus 1 by 6 lambda to the power 6, and then there is a d cube R12, d cube R13, and we have integrated over one of the volumes, that is d cube R23, and that leaves us with F12, F13, F23. So, where your B2 is given by 1 by 2 lambda cube d cube R f of R, which is what we have seen earlier. Okay. So, there is a integration over the volume. Okay. So, the partition function, the canonical partition function then can be written as Zn, this is for the sake of repetition. So, this is sum of all distinct n particle graphs. Okay. So, that is the definition of the partition function in this case. So, we have to calculate all these distinct n particle graphs. So, what is an n particle graph? So, an n particle graph is a product of the number of clusters so of which there are ml are L clusters. So, what it means is that we have M1 one particle cluster, that is there is no link, M2 two particle clusters, M3 three particle clusters, and so on. Okay. So, but there is a condition that you have to satisfy is that your L, that is the number of clusters multiplied by these ML has to be equal to, from 1 to n, has to satisfy the total n particles that are present in the system. Okay. So, once again these Zn, the partition function is sum of all distinct n particle graphs. And what is the definition of n particle graphs? So, an n particle graph is defined as the product of number of clusters, and there are ML of L clusters, which means there are M1 one particle clusters, M2 two particle clusters, and so on, subject to the condition this. Okay. So, let us call this as equation 1, where ML is equal to 0, 1, 2, and so on up till n. Okay. So, this condition has to be satisfied. In fact, it turns out that this condition is important, and it makes matter more complicated in the calculation of the partition function. So, just to remind you that this have to be counted separately. So, we have these this and this have to be counted separately. Okay. So, now notice this carefully. A given set of ML clusters satisfying equation 1, that is this equation. Okay. So, for a given set ML, with M1 one particle clusters, M2 two particle clusters, and so on. So, does not uniquely specify a graph. What it means is that this set actually denotes a bunch of graphs. Okay. So, let me give you an example. So, say 1, you have this what I just said. So, this, let me draw it once more. So, it is a 1, 2 and 3, and 1, 2 and 3, like these are different clusters, which is what you have learned. These are non-identical and different clusters, and 2 would be 1, 2, 3, and 1, 2, 3, and the connections are now given by this, and maybe this is 1. So, this is actually 4, and this is. So, by these examples what we want to say is the following, that there are in general many ways of forming an L cluster. Okay. So, so this set of integers ML, set of integers which are given by this ML, they specify a collection of graphs, not a single graph. This is what I want to say. So, let the sum of all the graphs corresponding to this set is denoted by this sum. Okay. So, then the partition function is written as, with of course V t, is written as sum over M L and S of M L. So, eventually it boils down to this sum of all the graphs corresponding to this set. Now, this of course, let us call it as equation 2, but this is not an independent equation, it has to be satisfied in conjunction with 1. Okay. So, that is what we have, and let us see how one can calculate these S of M L, so that we can deduce the partition function for the interacting case. All right. So, so the family of graphs that we need to consider emerge from one is that there are different ways of assigning n particles to the this ML cluster basically. Okay. And for any assignment, there are many different ways of forming the cluster. I mean, so basically see that for L greater than 2, there are 4 graphs and so on. I mean L equal to 3 rather, or rather L greater than 2, there are 4 graphs. So, this tells you the number of distinct ways, this is what we want to find, to assign n particles into this ml is given by n factorial divided by this. So, this 1 factorial divided into to the power m 1, 2 factorial to the power m 2 and so on. So, this is n factorial to the power the product of L equal to 1 to n and L factorial whole to the power m l. And so, m l is like m sub l, and this is equation number 3. Now, this is one of the key steps here. It tells you that number of distinct ways to assign n particles, and we will also find out that what are the values of each one of them. Okay. So, they are 1 factorial to the power m 1, where there are m 1 clusters of 1 particle each, 2 factorial to the power m 2, where m 2 is a number of 2 particle clusters and so on. So, this entire different ways that to assign these n particles into this ML set of integers, ML clusters, where ML satisfies this equation, which is LML summed over all L is equal to n. So, the number of distinct ways is equal to this, and the value of each term. So, the value of each term there in this different ways that we just said, this is equal to 1 B1 V 1 factorial, and it is a 2 factorial lambda cube B2 V whole to the power. So, this to the power m 1 to the power m 2 and 3 factorial lambda to the power 6 B 3 V to the power m 3 and so on. So, value of each of those terms is equal to that. So, S that sum over this set of integers m l is equal to n factorial, and then there is a product of L equal to 1 to n, and this can be written as V lambda to the power 3 L minus 3 into B L whole to the power m l, and this takes care of the counting process. So, that is your S of m l, and hence this is just the nothing but the partition function summed over m l, but of course, with the condition that we have discussed in 1. So, so this is equal to that. If you so S m l is equal to that, and we can simplify it further. We have a lambda to the power 3 n, and this is L equal to 1 to n, and there is a 1 by m l factorial, and we have this V over lambda cube B L whole to the power m l. Okay. It is the same expression. You can check that we have simply taken out this lambda to the power 3 n, giving you a lambda cube in the denominator here, and then all these B L terms are there, and there is counting of this m l factorial is also taken into account. So, that allows us to write down this Z n V t, which is equal to this m l and product of L equal to 1 to n 1 by m l factorial, and we have these V by lambda cube B L and to the power m l. So, we write this as equation 4, this as equation 5, and this as equation 6. So, we have been able to calculate as a sum over these set of integers m l, and this can be actually expanded to get term by term correction to the partition function or the non-interacting partition function that we have seen earlier. So, all these as I told, that is subject to this condition L m l L equal to 1 to n is equal to n. Okay. That is condition number 3 or equation number 3. Okay, so it's probably easier to write the grand partition function, because that factorizes in a more sort of easy manner. So that's a ZG. Now we no longer write it as NVT, so we write it as this fugacity, which is exponential beta mu and t, or you can just simply write it as mu. This becomes equal to n equal to 0 to infinity. This makes it easier, ZF divided by lambda cube whole to the power n, and now we have Zn Vt divided by this n factorial. Okay. So, that is the expression for the grand partition function, and this can be actually written as. So, let me see this ZF to the power n, this is equal to ZF to the power sum over L LML, because that is equal to n, and then this is equal to the product of L and ZF to the power L to the power ML. Okay. So, that gives us ZG, this is equal to M1 equal to 0 to infinity, M2 equal to 0 to infinity, and so on, and all these L clusters, I mean will be some ML going from 0 to infinity, and this is equal to 1 by M1 factorial and V over lambda cube ZF B1 whole to the power M1, and so this is one term, and the second term is 1 by M2 factorial, and we have a V over lambda cube ZF square B2 whole to the power M2, and so on, all these different terms. So, one can do more simplification. So, what one can do is that it is a 1 over V log of ZG ZF Vt, that can be written as 1 over lambda cube, and we have a L equal to 1 to infinity and a BL ZF whole to the power L. Just remind you that ZF is equal to exponential beta mu. Okay. So, this is this expression for the log of Zg, which is of course related to the grand potential. So, let us call this as 9, and so the equation of state is now easy to calculate. So, the equations of state it is nothing but because P over Kt is related to log of Zg. This is what we have extensively used when we did the quantum gases or ideal gases. Now, we are doing the same thing, excepting that they are non-ideal gases, and we have L equal to 1 to infinity, and you have a BL ZF whole to the power L. So, that is P over Kt, and N over V, which is equal to 1 over lambda cube sum over L equal to 1 to infinity, and you have a L BL and ZF to the power L. Okay. And this can be written as 1 by V by N is equal to this 1 over lambda cube L equal to 1 to infinity. So, let us say this is 10A, and we modify 10B a little bit by dividing on in the left, dividing by N, and L BL ZF L, this is nothing but equal to 1 over V. where small v is equal to v by n, called as a specific volume, and let us call this as equation 10b. So, equation 10a and 10b, which denotes the equation of state. So, these equations are called as the cluster expansion. So, 10a and 10b are called as a cluster expansion for the equation of state. Okay. So, that is the cluster expansion, and so basically this above discussion actually denotes the graphical representation of the perturbation series, which are basically denoted by the graphs. Okay. And the formalism is known as the link cluster expansion. Okay. All right. So, if we summarize, then what we have done is that we have found the sum of all these graphs, and this sum of all these graphs is basically nothing but the exponential of the sum of all these graphs. And now what we can do is that we can do for a dilute gas, which means v going to infinity, we can actually write down this B L of V t as in the limit v going to infinity to be B L some tilde and is a function of t. And so, using B L tilde, one can write down the equation of state as P over k t equal to 1 by lambda cube, and sum over L equal to 1 to infinity, and a B L ZF whole to the power L, and this is, let us call it as 11a, and 1 over the specific volume is equal to 1 over lambda cube, L equal to 1 to infinity, L B L tilde ZF to the power L, this is 11b. Okay. So, these are the equations of state in the case of a dilute gas, where we take this thermodynamic limit, that is v going to infinity. In fact, you can combine these two terms 11a and 11b and can write it as P v over k t, which is a more familiar form for writing the equation of state, and that is nothing but L equal to 1 to infinity A L of t and lambda cube by v whole to the power L minus 1, and let us call it as 12, and A L of t is called as the Lth virial coefficient. All right. So, this is the equation of state that we have gotten, but we still have not calculated all these integrals, and at least we should calculate 1 or 2 integrals in order to show that how the real equation of state or the van der Waals equation of state gets corrected due to this inclusion of the interparticle interaction, which is what we have calculated, or rather which we have committed ourselves earlier. So, what are the results of this virial coefficient and the cluster integrals? So, we need a relationship between virial coefficients which are A L t and the cluster integrals which are B L, and we can just simply write them as B L tilde because now we have taken this dilute limit BL tilde. So, this relationship is important, and the relationship can be obtained by just comparing the equation of motion, which is L equal to 1 to infinity and AL, and so there is this n equal to 1 to infinity, n b n. We are using this dummy indices n here because we can't have both L's, using them. That would create, that would mean that we are using same indices for both the cluster integrals and the virial coefficient. So, whole to the power n and this whole to the power L minus 1, this is equal to L equal to 1 to infinity. In this side, we do not mind writing it as L, because this is just a sum over L, there is a single sum, and this is ZF to the power L, and divided by L equal to again 1 to infinity, and we have L, BL and ZF whole to the power L. So, this can be called as equation 13, and now if we expand 13, we can write this as B1 tilde ZF plus 2 B2 tilde ZF square plus 3 B3 tilde ZF cube plus all these other terms, and then so that is the denominator going into the denominator of the right hand side of equation 13 going to the left hand side, and then we have a A1 plus a A2, then there is a sum n equal to 1 to infinity n b n tilde ZF to the power n, and plus A3 sum over n equal to 1 to infinity n b n tilde ZF to the power n whole square, and all these terms, that is equal to the numerator of the right hand side of equation 13, which is B1 ZF B1 tilde ZF plus B2 tilde ZF square plus B3 tilde ZF cube, and so on. In doing so, there is just one subtle remark that we have lost this information about the volume. So, it is very difficult to predict a phase transition based on this analysis. So, we want to stay away from the critical point, because the critical points would require you to have two volumes in the PV diagram for two different isotherms. It needs you to demarcate the relationship between the two volumes, but since there is no volume, this will not be relevant, or rather it cannot be it cannot predict a phase transition, and in fact it is more correct to say that we are away from the phase transition point, and this perturbation expansion or this graphical expansion that we have said is truly in the gaseous phase of matter and not close to the critical point. So, let us call this as equation 14, and so if you equate the coefficients of various terms, so various terms means equating the coefficients of ZF, we have A1 equal to B1 tilde equal to 1, A2 equal to minus B2 tilde, and A3 is equal to, this you can see term by term for powers of this ZF, 4 B2 tilde square minus 2 B3 tilde, and so on. So, these are the relationships between the virial coefficients and the cluster integrals. Okay. So, let us call this as equation 15. So, each virial coefficient which is AL, involves one or more cluster integrals. Which are BL tilde. Okay. So, this is the outcome of all this discussion, and let us now calculate the virial coefficients for at least one or two virial coefficients, at least one which is non-zero, and show that our analysis actually makes sense for the interacting gas. So, computation of the virial coefficients. Now, there we first have to notice that A1 equal to 1. So, which means that if you are at the lowest order, it does not give any correction to the gas. If you look at this expression of because your BL tilde is also equal to 1 for, so at the lowest level, that is L equal to 1 graph, then that gives you no correction, and it makes sense because then you are not considering any two particle graphs. So, ignoring all two particle graphs and onwards and above that means that we are talking about really one particle sector, and one particle sector is a non-interacting thing. So, we should simply get PV equal to NKT, which is the ideal gas law. So, this does not help. So, this tells you that even BL tilde, B1 tilde rather, is equal to 1. So, we need to at least go to the A2. So, and see that what comes. So, this is A2 is equal to minus B2 tilde, this is equal to 2 pi over lambda cube, and 0 to infinity 1 minus e to the power minus u r by k t, and this and the volume integral r square dr. Remember that because your u r is depends only on r, not the vector r, but the scalar r. So, we can do this volume integral which is usually like this, is equal to r square dr sin theta d theta and d phi. Now, if your integrand only depends on r, you can simply do this integral as 2 pi which is coming from phi, and the sin theta d theta integral can be done, and what we get is this 2 pi over lambda cube, this shown already. And now, we are going to put a specific form for u of r in order to calculate this explicitly. So, what specific form can we use? We can of course use the Lennard-Jones potential, which is that 612 potential that we have talked about earlier. However, that becomes more complicated. We also have proposed a simpler form where we have said that so use this. So, u of r is equal to minus u 0, which is the strength of the potential, n whole to the power 6. So, once again just to remind you that this is like this, and this is your r 0. So, at r lower than r 0, it is infinity. So, this is for r greater than equal to r 0, it is equal to infinity for r less than r 0. Okay. So, so this is like this part is okay, so let me okay. So, that is your u of r versus r, and that is the form that we can use. Of course, one can use the Lennard-Jones form as well, but the integral becomes more complicated. It is easier if we use it, and let us see what the A2 comes out to. So, your A2 becomes equal to 2 pi over lambda cube, and we have this as 0 to r 0, we have a r square dr, and we have a r 0 to infinity, we have 1 minus exponential u0 by kt. See, the minus sign becomes plus sign because there is a minus u0 there, and we have a r0 over r whole to the power 6, and then of course there is a r squared dr. Okay. The first integral is easy, that is just simply r squared dr, 0 to r0, and that gives you a r0 cube divided by 3 and so on. The second integral is a little complicated, but the second integral becomes easy. So, this is the first integral or the first term on the inside the the square bracket here. We have so let me use not this bracket, but there is another bracket here. Yeah. So, the second integral, if you make an approximation that your u0 by kt is much smaller than 1, this is called as the high temperature limit, and this has been told earlier that these are small but finite at large temperature. So, in that case what you do is that you write this as exponential alpha r0 by r whole to the power 6 and do a small expansion of this. So, this becomes alpha r0 by r whole to the 6 and so on. So, this 1 will cancel with this 1 that you see there, and the integral becomes particularly easy. You can write this then as a2 equal to 2 pi r0 cube, combining the two terms, which is 3 lambda cube 1 minus u0 by kt. And because of this approximation being used, and we call it as a high temperature expansion. This cluster expansion is also called as high temperature expansion. So, this is the form for the first non-zero virial coefficient, okay? And we have been able to calculate the cluster integral under some approximation, and that approximation, as we said, makes sense because this is the high temperature approximation for this particular case. So, at this level at the lowest order, lowest order means it is not the lowest, but the lowest one did not give any correction. So, this is equal to P equal to kt over V and 1 plus 2 pi r0 cube by 3 V. So, putting it into the equation of state, we get 1 minus u0 over kt, and this is the expression for pressure, and this can be written as so kt divided by V, and we have 1 plus B2 T V, and this B2 T is given by A2 lambda cube, which is equal to 2 pi r0 cube by 3. So, this is just a new name for the real coefficients. A2 was also a function of t. So, A2 t and multiplied by lambda cube. So, it is 2 pi r0 cube by 3 1 minus u0 by kt. Okay. Of course, we have found an expression for the pressure for an interacting gas, but whether it has two approximations inbuilt. One is that we have used this 6 potential, that is minus u0 r0 by r whole to the power 6, and then have taken the high temperature expansion. So, whether how reliable that is, one does not know unless one puts in all the information that we have obtained so far. And in fact, it turns out that if you do that, you get an equation of state for which has a form like this 3 v square, this is equal to k t over v 1 plus 2 pi r 0 cube by 3 v. Okay. And if you send it to the other side, you will have to make this thing as 1 plus 2 pi r 0 cube by 3 v going to the other side, and then using this expansion that this is equal to 1 minus 2 pi r 0 cube by 3 v. You will see that this has a remarkable similarity with the van der Waals equation of state, and then it can be written as a p plus really a by v square, that is the specific volume, and then v minus b is equal to k t. Okay. And we have 1 plus 2 pi r 0 cube by 3 v. This is equal to 1 minus, so this is what we have used there. We have already written that. So, let me sort of skip this. So, this is where it comes from, and sorry, a is equal to 2 pi r 0 cube u 0 divided by 3, and b is equal to 2 pi r 0 cube by 3. So, even with this approximation that we have done, that is using this potential as u of r equal to minus u 0 r 0 by r whole to the power 6, and the high temperature expansion which came in the form of ignoring, or rather using this u 0 by k t to be much smaller than 1. So, we still get the equation of state to resemble very closely or almost similarly with these definitions of A and B to be of this form, but nevertheless it sort of mimics the equation of state. So, this is the power of, or the utility of this linked cluster expansion, and we have been just able to calculate one integral, the first non-zero or the first correction, so to say, because the lowest order really did not give any correction, the one that gives correction. So, let me rephrase this lowest order that would give correction. Correction to what? Correction to the non-interacting limit. Okay. And if you want further expansions, right, more correct expressions for that, then you have to calculate all these B3 and so on. So, these A3 is in terms of B2 and B3 and so on. So, we calculate A3 and then we calculate A4 and so on. So, these would require us to calculate B2, B3 and more farther range of these Fij's have to be calculated, or they have to be taken into account. This would lead to more and more complex integrals, but nevertheless it can be done. The primary idea of this is pretty pedagogical, that we want to show that using this linked cluster expansion one can take into account the interaction effects. So, towards the end of this course, we have talked about a number of interacting problems. I mean, starting from this renormalization group, transfer matrix, mean field theory, Bethe ansatz, and then the linked cluster expansion. Some of them are nicely applicable to the these spin systems, which also denotes the paramagnet to ferromagnet transition and so on and so forth. However, this linked cluster expansions are relevant for regions which are far away from these phase transitions, and we are truly in the gaseous phase, but nevertheless it is an elegant technique that that allows you to calculate the more and more improved equation of state, compared to the ideal equation of state, which is PV equal to KT. Okay. So, I hope the intention is clear and the calculations are clear. It involves really 2 steps to be correctly found out, and these are the 2 steps. Okay. So, these are the 2 steps. This is step number 1, that is finding out the distinct ways to assign n particle into this various kind of clusters, and then of course, these number 2 that you got is what are the values of all these clusters and so on. We were here. So, the values of each term is what is important. Okay. So, this is the next important thing. If you understand this and these assignments of various formation of various clusters, then calculating the partition function is only bringing out a series expansion in terms of this cluster coefficients or these cluster integrals. And then of course, pertaining to certain approximations, we can always have a potential function, and then it just simply reduces to calculating more and more complicated integrals. And suppose if we cannot do it by hand, we can use numerical method, numerical means to calculate these integrals, but nevertheless you finally get what you want, that is what's the equation of state for an interacting gas for an arbitrary form of interaction. So, I will stop here for today. Thank you.